So go ahead and take a look at problem number 9. At the very least, I want you to try all part A on your own. Parts B and C, maybe you're not exactly sure how to sketch out the graphs, or maybe you want to try them on your own. Either way, I'm going to go through all the solutions. So try all part A on your own, come back to see the solution. Okay, so now that we're starting to get more into the kinematics problems, you'll see that there are a lot more ways, a lot more options for solving the problems, and that's why I've also given a variety of different answers here, because depending on which equations you use, you might get any one of these answers. And that's one of the things you really want to realize, especially in physics, is that since there's so many different ways to go about solving the problem, if you get an answer that's just a little bit different from someone else, or maybe from the published answer, there's a really good chance you still did it correctly. Maybe you just rounded a little bit differently somewhere, or maybe the person who solved it and published the answer didn't use the same equations you did, but as long as you're close, you're just fine. Okay, so we've got Timmy on the bicycle, starts from rest, speeds up through the intersection. First thing you want to do is find his acceleration. So there's a bunch of different ways to do this, and in fact, you don't even have to go in the order that the problem tells you to go. But for one way to go about doing this is one-stop shopping equation is to use delta x equals v naught t plus half at squared. For some reason, I find most students tend to forget to use this equation in this particular problem, but this is really a one-stop problem here, because we know that he starts from rest, so it means his initial speed is 0. Anything times 0 is 0, so that means the whole first term v naught t goes away, and then we're left with delta x equals 1/2 at squared, which means we can just rearrange this immediately for acceleration, because we have how far he goes and we have the time. So of course you want to do your algebra first, move the 2 over there, divide through by t squared. This equation rearranged looks like a equals twice delta x over t squared. You know, he moves 12 meters in the 3.41 seconds, and you should have no problem getting 2.06 meters per second squared. So if we're going in order, the next thing to do is to find how fast he's moving at the end of this motion. That we're moving the 12 meters or 3.41 seconds. So there's a bunch of options here as well. You can use Vf equals v naught plus at. That's the acceleration equation rearranged for final speed. Once again, initial speed is 0. Use the acceleration you just found times the 3.41 seconds. You're going to get one of those answers. So either 7.02, 7.03, or 7.04 meters per second. I give all those answers because there are other ways to do this. For example, if you use the time-independent kinematics equation, Vf squared equals v naught squared plus 2a delta x, take the square root of both sides, because of course we're solving for Vf. Once again, we see that v naught equals 0, so that goes away. We just found the acceleration, we know his displacement. If you put this in, you're again going to get something in the order of 7 meters per second. So there's always options here. That's why, different ways of doing it are going to give you slightly different answers, but they're all really the same value. Now, other students may say, you know what, I want to find the final speed first. I don't know how to find the acceleration. Well, there's ways to do that as well. For example, if you use v bar equals delta x over t, and of course it is always v bar, well, we have the distance, we have the time. Now, be careful. Dividing distance by time does not get you what you want. It doesn't get you Vf. It gets you v bar, which is the average speed. You then have to pair it with another equation, in this case v bar equals v naught plus Vf over 2, where once again v naught equals 0, to find Vf. So if I just set these two equal to each other, delta x over t equals Vf over 2, I'm sure you can be able to see that then Vf equals twice delta x over t. You can put this in immediately with the displacement of 12 meters and the time of 3.41 seconds and get the final speed again somewhere around 7 meters per second. But we hadn't found the acceleration, so what do? Well, now you can go backward. Now you can take the original acceleration equation, plug in the final velocity you just found, and you can find the acceleration this way, and you're going to probably get something around 2.06 meters per second squared. See, though there's many, many options here, and there's not just one correct way of doing it. And I show you all the different options because one way will work for one student, one way will work for another student. But also, once you find one way that works, you may want to explore other options. We might say, you know what, the way I'm doing it right now is sort of working for me, but oh, I like that one a little bit better. I'm even better at using that equation. And so just, try to find as many different ways of doing it, what you feel most comfortable with, as long as you're successful. Okay, so we're going to get into the graphs. Now, if you haven't had a chance to do the graphs yet, now is a good time to pause the video and sketch these out. It says to label the axes where appropriate, so you have to label some numbers, some of the important points for the numbers we've calculated here. But other than that, you're just looking for the general shapes. Okay, so first of all, I'm going to label the fact that we know that the time for this problem ends at 3.41 seconds, so I'll label that on the time axis for both graphs, position and velocity. And we know for the position, well, he's got to go 12 meters, and for the velocity, we know he's going to end somewhere in the range of 7 meters per second. So I'm going to label those ending position and velocities as well. I just picked 7.04 meters per second, but remember, it's somewhere around 7 meters per second, depending on what you actually calculated, so you can label whatever you want. Okay, so now the question is, what are the shapes going to look like? Well, let's actually start with the velocity versus time, which I think is actually a little bit easier. We know he starts from rest, so we know that no matter what, it's going to start at 0, 0. When time equals 0 is velocity equals 0, and we know at 3.41 seconds it's going to get to something around 7 meters per second. What shape is it in between? Well, here's where you have to be thinking about all the connections among the graphs. So we know that the acceleration is uniform, right? It says it uniformly speeds up. Uniform means constantly, not changing. So now you say to yourself, okay, it's a not changing acceleration, and we're looking at a velocity versus time graph. So what is acceleration on a velocity versus time graph? Well, one of our connections is that the slope of velocity versus time is acceleration. Okay, good. So we know that the acceleration is going to be represented by the slope. So how does that help us with the shape? Well, then we say to ourselves, wait a second, we know that anytime you have a constant slope, you've got a straight line, right? All straight lines have constant slope. So we're going to put it all together. The acceleration is represented by the slope. The acceleration is constant, and constant slope means a straight line. So what shape are we going to be having here? It's going to be linear with a positive slope. In case that still doesn't make sense, I'll sort of go backwards now. Okay, so we know we started from rest, so when time equals 0, velocity equals 0. I drew linear with a positive slope, so it's a straight line. All straight lines have constant slope. It's a velocity versus time graph. Slope represents acceleration, and the problem tells us he uniformly speeds up. That means constant acceleration. In this case, straight line on velocity versus time. Now, what about the position versus time graph? Well, here we say to ourselves, what does slope represent on position versus time? Slope represents velocity. What was happening to his velocity? Well, he was speeding up. He's getting faster and faster and faster, gaining 2.06 meters per second for every second that goes by. So now you say to yourself, well, how does that connect? Well, if the slope represents velocity, and the velocity is increasing, that means we're looking for a graph that has an increasing slope. What would that look like? That's going to be a shape like this. In this case, that's going to be a parabola opening upwards. You should be able to see if you were to maybe take a straight edge, and maybe right now actually take your pen or pencil and put it right up against the screen here, or against the parabola you've drawn on your paper. You should see that if you put it against here, it's a pretty shallow slope. If you put it over here, it's a steeper slope. If you put it over here, it's an even steeper slope. So that means that the slope keeps getting larger and larger and larger. The slope represents velocity. This means that this object has an increasing velocity. The slope gets steeper and steeper. And that's that connection among the graphs. Now, how do we know it's a parabola here? Well, that actually takes some calculus, and we're not really going to get into it in this class, but it's just a good thing to know that if, for example, we have a straight line on velocity versus time, we're going to have a parabola on position versus time.